the last lecture I introduced two basic concepts of point estimation, namely unbiased estimation and consistency. One of the properties, that is unbiasedness, it is related to the estimator being equal to the true value on the average. That means, if we have many samples, then the average of that will be equal to the true value. Whereas, consistency is a large sample property. That means, if we take a sample to be large enough, then the probability that it is close enough to the true value of the parameter is almost equal to 1. And so, the two properties have somewhat different applications and as well as implications, and many times we try to combine various properties of the estimators. So, I had shown in the last lecture some sort of invariance of the consistent estimators. For example, if t is a consistent estimator for theta, then g of t n, where g is a continuous function, will be consistent for g theta. Similarly, if I have t n to be consistent for theta and I have sequences of numbers a n and b n such that a n converges to 1 and b n converges to 0, then a n t n plus b n also is a consistent estimator for theta. So, let me give a few examples. Let us consider, say, let x 1, x 2, x n be a random sample from an exponential distribution with a location parameter mu. That means, I am considering the density function of say x I to be e to the power mu minus x, where x is greater than mu and 0 otherwise. So, this is actually the well known shifted exponential distribution. Here mu denotes the minimum guarantee time of the component or the life. So, here if you see, expectation of x I is equal to mu plus 1. So, mu plus 1 is the first moment, and therefore, if I consider expectation of x bar, that is also going to be mu plus 1. So, by weak law of large numbers, we get x bar as a consistent estimator for mu plus 1, and if I take 1 to the left hand side, then we get, let me call it T 1. So, T 1 is equal to x bar minus 1 is unbiased and consistent for estimating mu, that is the minimum guarantee time. Now, in this problem, let me introduce another estimator. Let us consider, say, y is equal to x 1. Here this x 1 denotes the minimum of the observations x 1, x 2, x n. One can derive the distribution of x 1. In fact, in general, if I want to find out the distribution of this, I can find it in the following way. I consider, say, CDF of this, that is probability of x 1 less than or equal to x. This can be written as 1 minus probability of x 1 greater than x, that I can write as 1 minus probability that, now if the minimum is greater than x, this is equivalent to saying each of the x i's are greater than x. Now, here x1, x2, xn is a random sample, therefore, x1, x2, xn are independently and identically distributed random variables. So, this can be actually written as 1 minus probability of x1 greater than x into probability of x2 greater than x and so on, probability of xn greater than x. That is 1 minus probability of x1 greater than x to the power n. That is equal to 1 minus. Now, this is again 1 minus CDF of x1 itself. Now, if I have this as the probability density function, I can write down the corresponding CDF here, that is integral from mu to x of e to the power mu minus t dt that is equal to 1 minus e to the power mu minus x. So, if I substitute 1 minus e to the power mu minus x here, I will get 1 minus e to the power n times mu minus x. So, the probability density function of x1 is, now this can be obtained by considering derivative of this. Of course, this value I have written for x greater than mu. If x is less than mu, then this is going to be 0. So, if we consider derivative of this, I will get the density function of x1 as n times e to the power n mu minus x, where x is greater than mu. So, this is the probability density function of the minimum of the observations if I have considered a random sample from an exponential distribution with a location parameter mu. Now, this is the usual 2 parameter exponential distribution. Here the scale parameter is 1 by n and location parameter is mu. So, if I consider the expectation of x1, that is equal to mu plus 1 by n. So, if I take T2 as x1 minus 1 by n, then T2 is also unbiased for x1 for mu. So, I have got another unbiased estimator. Now, in this one I can consider variance also. What is variance of x1 for example? Variance of x1 here is 1 by n square. So, variance of T2 is also 1 by n square, because it is variance of x1 itself. The variance of a function does not change if I make a change of origin. Now, consider the result that if expectation is equal to the parameter and the variance goes to 0, T2 is unbiased and its variance goes to 0 as n tends to infinity. So, T2 is also consistent for mu. So, in this problem we have considered 2 estimators. One is based on the sample mean, this is unbiased and consistent, and at the same time we have considered T2 which is based on the minimum of the observations, this is also unbiased and consistent. So, that brings us to the question that if I have more than one estimator satisfying certain given desirable properties, then which one we should use. So, In this direction I will give you one more example. Let us consider say x 1, x 2, x n be a random sample from a uniform distribution on the interval 0 to theta. That means, I am considering the density of x I as 1 by theta, 0 less than or equal to x I less than or equal to theta, it is equal to 0 otherwise. Now, in the uniform distribution, we know expectation of x I is the middle point of the interval, that is theta by 2. So, immediately we conclude that expectation of x bar is theta by 2. This implies that expectation of 2 x bar is equal to theta. So, if I call T 1 is equal to 2 x bar, then T 1 is unbiased and consistent for theta. Now, in this problem let me consider another one. Let us consider say x n. Now, x n I am calling to be the maximum of the observations. As in the previous case, we can derive the distribution of x n. Let us consider the CDF of this. So, this is equal to probability of x n less than or equal to x. Now, this statement that the maximum is less than or equal to x is equivalent to that each of the observations is less than or equal to x. And once again using the fact that x i's are independently and identically distributed, this is equivalent to saying each of the x i's CDF at x. So, this is simply this to the power n. Now, for the uniform distribution, the CDF is it is equal to 0 if x I is less than 0, it is equal to x by theta if 0 is less than or equal to x is less than or equal to theta, it is equal to 1 if x is greater than theta. So, if we use this CDF here, this becomes 0 if x is less than 0, it is equal to x by theta to the power n if 0 less than or equal to x is less than or equal to theta, it is equal to 1 if x is greater than theta. One may find out the probability density function from here by considering the derivative, because this is a continuous distribution. So, you get the density function as n x to the power n minus 1 by theta to the power n if x lies between 0 to theta and it is 0 otherwise. Let us consider say expectation of x n now. So, expectation of x n is equal to integral x into the density function of x n from 0 to theta, that is equal to integral 0 to theta n x to the power n by theta to the power n dx. So, as we can see easily, the integral of x to the power n will be x to the power n plus 1 by n plus 1, and if we substitute the limits from 0 to theta, I will get theta to the power n plus 1, and in the denominator I have theta to the power n. So, that will cancel, and therefore, this value will be equal to n by n plus 1 theta. If I adjust this n by n plus 1 on the left hand side, I get this is equal to theta. So, if I use the notation T 2 as n plus 1 by n x n, then T 2 is unbiased. We had obtained estimator T 1 as 2 x bar, which is unbiased, and now I have obtained T 2. Let us check say probability of x n minus modulus theta greater than epsilon, whether it tends to 1 or not. That we can check from here also. If we take the limit of this cumulative distribution function, now here x is less than or equal to theta. So, this value will tend to 0 if x is less than theta, and whenever x is greater than or equal to theta, it is becoming 1. So, if I take the limit of, if I consider say limit of f x n as n tends to infinity, then this is equal to 0 for x less than theta and it is equal to 1 for x greater than or equal to theta. Now, this denotes the distribution of a random variable which takes value only theta. This is the CDF of a random variable which takes value theta with probability 1. So, basically we have proved that x n converges to theta in distribution, but theta is a constant, therefore, it is equivalent to saying x n converges to theta in probability. In fact, this fact can also be proved in a different way. I will consider directly the definition of convergence in probability. Let me take say probability of modulus x n minus theta say greater than epsilon. Now, the distribution of x n is in the interval 0 to theta, that means x n is always below theta. So, if we consider this modulus of x n minus theta, this is same as theta minus x n. So, this is equivalent to probability of theta minus x n greater than epsilon, which I can write as probability of x n less than theta minus epsilon. Now, this is nothing but the distribution function of x n at the point theta minus epsilon. Since x n is having a continuous distribution, whether we put less than or equal to, it does not make a difference. Therefore, this value is equal to theta minus epsilon by theta to the power n, as we have derived just in the previous sheet here. So, now you can see here epsilon is a positive number. So, theta minus epsilon is less than theta. Therefore, if I take the limit as n tends to infinity, this will go to 0. So, x n is consistent for theta. Let me call it T 3. If we look at the coefficient n plus 1 by n, this goes to 1 as n tends to infinity. So, we have the result that if T n is consistent for theta and a n goes to 1, then a n T n is also consistent. Therefore, if we use this fact, T 2 is also consistent for theta. So, T 2 is unbiased and consistent, T 1 is also unbiased and consistent. So, I have given you two different distributions, where for estimating of one parameter I am getting two different unbiased and consistent estimators. So, that shows that actually we need additional criteria to distinguish between or to choose between various competing estimators. From the previous two exercises, we can also find something more important. If we look at the form of the distribution function of the maximum and the minimum, there is some specific structure here. For example, when I took the limit here, I got only 0 1 here. Similarly, in the distribution of the minimum, we had that x 1 is converging to mu. So, minimum was converging to the lower limit, and here the maximum is converging to the upper limit theta. In fact, if we have any continuous distributions, then this is a general fact. So, I will state it in the following results. So, let me give it as exercise. Let x 1, x 2, x n be a random sample from a continuous population with CDF say capital F x, and the range of variables is interval a to b. Of course, this interval may be open or closed, that does not make any difference if we are handling a continuous distribution. Let us define say u is equal to the minimum and v is equal to x n. Then the claim is that u is a consistent estimator for A and v is a consistent estimator for B. So, the proof will use the steps which we have derived just now, that is the CDF of u, that is 1 minus. So, actually it is equal to 0 for x less than A, it is equal to 1 minus f u to the power n for A less than or equal to x less than B, it is equal to 1 for x greater than or equal to B. Similarly, if I consider say f v, then it is equal to x 0 for x less than A, it is equal to f v to the power n for A less than or equal to x less than B, it is equal to 1 for x greater than or equal to B. Notice here that this equality or inequality does not make any difference here, because it is continuous distribution. So, if I take the limits here, now f is a number between 0 to 1. So, if I take the limits here, this number will go to 0. So, this is going to 1. So, if I take the limit as n tends to infinity of f u, I am getting 0 for x less than A and it is equal to 1 for x greater than or equal to A. So, this is CDF of a random variable which is simply degenerate at A. So, we can conclude that u converges to A in distribution and therefore, u converges to A in probability, because convergence in distribution and probability are equivalent if the right hand side is a constant. Similarly, if I consider limit of f v as n tends to infinity, then this is also 0 for x less than b and it is equal to 1 for x greater than or equal to b. So, once again v is converging to b, this random variable is degenerate at b. So, v tends to be in distribution or v tends to be in probability. So, if a continuous distribution is having a range a to b, then the smallest order statistics converges to the lowest value or the lowest value in the range, and the largest order statistic converges to. So, these can be treated as the consistent estimators of these respective parameters. This actually gives some easy applications basically. For example, we want to find out a consistent estimator for the range. For example, here range may be b minus a. then easily you can say that V minus U, that is the maximum minus the minimum sample range, is the consistent estimator for the population range. As a consequence, we conclude that the sample range, that is x n minus x 1, is consistent for the population range B minus A. We have some further special cases here. For example, lower limit could be minus infinity or the upper limit could be plus infinity. In that case, for example, if the lower limit is minus infinity, then x 1 does not converge in probability. Similarly, if the highest value is unbounded, that means b is infinity, then x n does not converge in probability. Next, we introduce the concept of efficiency. As we have seen that there can be situations where we have more than one consistent estimator, we may have more than one estimator which is unbiased as well as consistent. So, in that case we introduce the concept of efficiency of estimators. For judging the efficiency of the estimators, we consider something called as expected error. We have seen unbiasedness. So, in unbiasedness we had expectation of t is equal to the given parametric function, say g theta. So, if it is not unbiased, expectation of t minus g theta is a bias, or you can say expected error. But in there is a danger in using bias as a simple criteria for goodness of an estimator, because sometimes the negative bias and the negative errors and the positive errors may cancel out each other. So, on the average the estimator may become unbiased, but actually it is not a good estimator. We have seen the examples, for example, in the estimation of e to the power minus 3 lambda, we had an estimator minus 2 to the power x in Poisson distribution, which was taking values always away from the range, but the errors were positive and negative both, very large errors, and they were cancelling out each other. So, simply using expectation of x minus g theta, that is bias, as a measure is a dangerous thing. So, one may look at other measures. For example, why not consider absolute error and then take expectation. So, one may consider expectation of say t minus g theta absolute value. So, this is called the mean absolute error. Or one may consider expectation of t minus g theta whole square, which is called the mean squared error. So, I will pay some attention to this in the definitions. In the first case, we are simply looking at the amount, or you can say magnitude of the error that we have committed in estimating g theta by t, and then we take the average of that. In the second one, we are considering the squares. So, if you think as a layman, then probably we feel that the first one is an appropriate measure for the error, or you can say average error. However, in practice the evaluation of expectation of modulus t minus g theta is quite complex. Second point is that if we look at mathematically, this function is not easy to handle. The main problem is that modulus function is not a smooth function, because it is having a corner, that is at t is equal to g theta, it is not smooth. Whereas, if we look at the mean squared error, it is easy to evaluate and it has a simple interpretation which is quite. So, what I do, I add and subtract expectation t here. So, let us consider this as one term and this as one term. So, this becomes expectation of t minus expectation of t square plus expectation of t minus g theta expectation of that square plus twice expectation t minus expectation t into expectation t minus g theta. So, let us look at these terms. The first term is simply the variance of t. The second term is fixed term. So, expectation will be the same value, because we have already taken expectation here. This term is nothing but the bias of the estimator t. And if you look at the cross product term here, then this term is a constant. So, expectation applies to this and this becomes 0. So, we have that mean squared error, let me call it MSE of t, that is equal to variance plus the bias. Now, this is quite significant interpretation. If I have two estimators, say T 1 and T 2, and we only say that variance of T 1 is less than variance of T 2, then we are controlling only one quantity. However, it may turn out that there is another estimator, say T 3, which may be actually biased, but its variance is much less. So, that the overall mean squared error is smaller. So, the average squared error will be less. So, one can use mean squared error as a good criteria for judging the goodness of an estimator. So, we will say that we can say that estimator, say T 1 is better, which is actually a terminology for more efficient than T 2 if mean squared error of T 1 is less than or equal to mean squared error of T 2 for all theta. So, if the two mean squared errors are equal, then they will be same. Now, in the context of unbiased estimation, this concept of mean squared error being smaller is equivalent to variance being smaller. For example, if the estimator t is unbiased, then bias will be 0 and this mean squared error will be equal to the variance. If t is unbiased for g theta, then mean squared error of t is called to be variance of t. Now, we define uniformly minimum variance unbiased estimators, that is UMVUE. So, an estimator W is said to be UMVUE of say g theta if W is unbiased and for any other unbiased estimator, say W star of g theta, variance of W will be less than or equal to variance of W star. That means, it will have the minimum variance throughout the parameter space. The first result in this direction is about the uniqueness of the UMVUE. If so, we also use the terminology best unbiased estimator, etcetera. So, if W is UMVUE of say g theta, then W is unique almost everywhere. So, let W star be another UMVUE. Then by definition, expectation of W, expectation of W star both are same as g theta, and variance of W and variance of W star are also same. Let us call it say sigma square. Fine. Now, let me define say W 1 as half W plus W star. Then what is the variance of W 1? We can apply the formula for a linear combination of variables. So, variance of a constant times that constant square times variance of W plus W star, which is becoming variance of W plus variance of W star plus twice covariance between W and W star. Now, we are assuming variance of W and variance of W star to be sigma square. So, it becomes 1 by 4 2 sigma square plus twice covariance W W star. Now, covariance square is less than or equal to the product of the variances, the well known Cauchy-Schwarz inequality. So, this becomes 1 by 4 2 sigma square plus twice square root of variance W into variance of W star, but these are both sigma squares. So, this is simply becoming sigma square. So, 2 sigma square plus 2 sigma square. So, it becomes sigma square, which is the variance of W or W star. So, what we are proving? If W is UMVUE, W star is another UMVUE, then I am able to get another estimator W 1, which is also unbiased, because if I take expectation of W 1 here, that is again g theta, as both W and W star are unbiased, and its variance is less than or equal to the variance of W. So, let me call this equation number 1. Inequality in 1 is not possible, because our original claim is that W and W star are UMVUE. So, another unbiased estimator cannot have variance less than them. So, at the most it can have equal. So, that means we should have equality. Now, how this inequality came? Inequality came from this condition of the correlation between W and W star being less than 1. So, that means correlation must be 1, that is covariance is equal to the square root of the variances. That means W and W star are linearly related with probability 1. So, for equality to hold, W star must be linearly related to W with probability 1. Now, once again you have unbiasedness. So, if you are saying unbiasedness, then what should be the condition here? And also if I look at say covariance here between W and W star, then that is equal to covariance between W and a theta w plus b theta. So, that is equal to a theta into sigma square. So, that means, because this covariance between w w star is equal to variance w. So, a theta is 1 and b theta will be 0, because unbiasedness is there, because expectation w star must be a theta. So, that is simply becoming g theta plus b theta. So, b theta must be 0. So, what we are concluding here, that w is equal to w star with probability 1. That means, w is unique almost everywhere. So, you can't have two different unbiased MVUEs. If they are two different, then they are equal almost everywhere. Now, next I give a necessary and sufficient condition for an estimator to be UMVUE. So, let us consider, let U g be the class of all unbiased estimators of g theta. Let U 0 be the class of all unbiased estimators of 0. So, we have the following necessary and sufficient condition. So, T belongs to U g with variance of T to be finite. So, this has minimum variance at theta is equal to theta naught if and only if covariance of T with say f is 0 for every f belonging to U 0, for which variance of f is finite. That means, if an estimator is having covariance 0, that means, it is uncorrelated with every unbiased estimator of 0, then this will be UMVUE of a function g. Let me prove this here. So, let T be unbiased estimator of g and its variance be finite, and let variance theta naught T be minimum. Now, let us consider f belonging to U 0 such that covariance between T and f is not 0. So, I am assuming contrary to what we have to prove. So, we will arrive at a contradiction. So, let us consider say T plus lambda f. Now, if I take expectation of T plus lambda f, then it is equal to expectation T, that is g theta, plus lambda times expectation f, that is 0. So, it is equal to g theta. So, this new function which I have created T plus lambda f is also unbiased. Now, let us take variance of T plus lambda f. So, that is equal to variance of T plus lambda square times variance of f plus twice lambda covariance between T and F. Now, if I put a condition here that this is less than variance of theta naught T, then this thing cancels out and it is reducing to a quadratic being less than 0. That means, this condition is equivalent to lambda into lambda v theta naught f plus twice covariance theta naught T f less than 0. So, this condition obviously can be satisfied. The condition 2 is satisfied for 0 less than lambda less than minus twice covariance T f by variance f. Of course, all these evaluations are at the point theta naught. If covariance of T and f is negative, and for minus twice covariance theta naught T f by variance theta naught f less than lambda less than 0, if this is positive. That means, whatever be the value of covariance between T and f, whether it is positive or negative, I am able to obtain a range of lambda values such that the variance of T plus lambda f is less than variance of T. This is a contradiction to the fact that I assumed that variance of T is minimum at theta naught. So, where is the mistake? The mistake is that I am assuming that covariance between T and f is not 0. So, this is wrong. So, this contradicts the fact that variance theta naught T is minimum. Hence, we must have covariance between T and f equal to 0. Now, let us take the converse of this. Conversely, between T and into variance of T prime. So, obviously, this is equivalent to saying that variance of T is less than or equal to variance of T prime. So, if I am taking covariance of T to be 0 with every unbiased estimator of 0, and I am taking another unbiased estimator T prime of g theta, then I am getting that the variance of T is less than or equal to variance of T prime. This proves that T has minimum variance at theta naught. Another thing which you can conclude from here, I have proved that if T is UMV UE, then covariance between T and T prime, that is equal to variance of T. That means, this is always positive. So, we are also concluding from here that the covariance, or you can say correlation between the UMV UE and any other unbiased estimator is always positive. Another interesting property about the UMV is that if T1 and T2 are UMV UEs of G1 theta and G2 theta, respectively, then A1 T1 plus A2 T2 is UMVUE for A1 G1 theta plus A2 G2 theta. That means, some sort of linearity property is also true for the UMVUE, although it is true for the unbiased estimation, but it is not clear that it will be true for UMVUEs, but that is true here. In fact, one can look at a very simple proof of this. If I consider, say, covariance of A1 T1 plus A2 T2 with an unbiased estimator of 0, then it is equal to A times covariance between T1 and F plus A2 times covariance between T2 and F. Now, if T1 and T2 are UMVs, these are 0. So, this is simply 0. So, by the previous theorem, this result follows. As an application of this theorem, let us consider linear model and try to obtain UMVUE. So, let us consider the Gauss-Markov linear model. So, y is an n by 1 vector with mean x beta and variance covariance matrix as sigma square y. So, actually it is the part of the Gauss-Markov linear model where we write it as plus epsilon, and epsilon follows normal 0 sigma square I. So, let us consider, say, h y be a real valued function such that expectation of h y is, say, 0 for all beta. This may be, say, n by p, this may be p by 1, etcetera. So, if you write this statement expectation h y is 0, it is equivalent to h y into the density function of y. This is a multivariate normal distribution. So, it is e to the power minus 1 by 2 sigma square y minus x beta prime y minus x beta, and some coefficient will come which I am writing as a constant. This is equal to 0 for all beta belonging to R p. This is a multivariate integral here. Now, you differentiate both the sides with respect to beta, then I will get h y, then derivative of this will give this term into the derivative of this with respect to y, that gives me x prime y e to the power minus 1 by 2 sigma square. In fact, here I can simplify beforehand. I can write the term which is not involving y, I can separate out and take to the other side. So, this is reducing to so, if you differentiate this, you will get x prime y here and the same term here. So, this is equivalent to saying expectation of h y into some coefficient lambda prime x prime y is equal to 0 for all lambda belonging to R p. So, what is this one? This is a linear function. So, by the previous theorem, what we are saying is that lambda prime x prime y is UMVUE of expectation of lambda prime x prime y, that is lambda prime x prime beta. In the Gauss-Markov theory of linear models, we had proved that lambda prime x prime y is the best linear unbiased estimator of lambda prime x prime beta. Here we are proving that it is not only best linear unbiased, it is actually best unbiased, that is, it is the UMVUE for this. Although I have made a small mistake here, it is lambda prime x prime x beta here. So, for this it is becoming best unbiased estimator. In the forthcoming classes, we will consider methods for finding out estimators. Just now in the previous two classes, we have considered the properties of the estimator, some desirable criteria. However, there must be some methods by which we can derive these estimators. So, we will do some well known methods, and as well as we will explore further how to find out the best unbiased estimators